The plan for today is that we are talking quite a lot about model selection, model testing, and MCMC, and a little bit about data partitioning. So that is the plan for the entire day. I hope you recovered from yesterday and are fresh for a full new day of a lot of new ideas. But as I said yesterday, we are going to repeat the same type of models today, so that all what we talked about yesterday can sink in better and you get a better understanding and handle of how to use RevBayes for doing your phylogenetic analysis. So in model testing, there's generally like two major purposes. One is actually that we want to select a specific model, or we want to test a specific hypothesis. So this is what I put in the category of model selection, because we have a set of models and we're selecting the best model among that set of models. That is the main topic of this morning. The other part is model adequacy testing, or testing of the absolute model fit, which will be part of the afternoon session, where we actually want to just test for a single or specific model, which could be the best model that we chose from our set of models, and test then actually does that or does our data fit to the model that we used? Is the data probable under that specific model? And a little bit like the examples for model selection or hypothesis testing could be if we want to test for a correlation between speciation and extinction, and then we estimate the correlation and extinction, and here we see that we have a negative correlation, whereas here the correlation as well, it's negative positive. So you see here the posterior distributions of the parameters that we estimated, and then the task would be to actually see, well, is it actually significantly like that there's a negative selection, or is it significantly different from zero? And in this example, you could see that here it's out in the tail of our posterior distribution, so you would actually expect that you have a negative correlation to the speciation rate. So that is when we do hypothesis testing. The other example from the tutorial yesterday was when we actually just want to estimate the phylogenetic tree, and there's quite a lot of different substitution models that we could choose. So which substitution models should we select? Because from the tutorial yesterday, one of the results that we should have seen is, depending on which substitution model we use, like if we use a really simple substitution model like the Jukes-Cantor substitution model, then we get a different phylogeny than if we use a very complex or more complex substitution model like the GTR plus gamma model, then we would get a different topology. So in that case, we also need to do a model selection to just get a different estimate, although in this case we're not really primarily interested in the models that we are selecting, because we don't really actually care if the best model is a GTR plus gamma or a Jukes-Cantor model. We're only actually interested in the phylogenetic tree. But still we need to do sort of the same type of analysis. And here we can show a little bit what the general idea is, that if we're using a much too simple model, then we're getting biased parameter estimates. But if we use a more complex or too complex model, then we are overfitting that model to the data that we have, and the variance in our parameter estimates, or because we are overfitting it, it is trying to capture too much information, and we're also getting wrong estimates. So the best idea would be that we're somewhere in the middle here between having too few parameters and therefore a small bias, and not too many parameters, so that we're not overfitting to the data. So this is the goal why we do a model selection, if we're just really interested in finding the best fitting model. The outline then here is I'm going to talk a little bit about the frequentist inference, because I think that many of you might be more familiar with these concepts like likelihood ratio tests, AIC, BICs. And then I'm going to talk about Bayesian inference, so Bayes factors, and specifically how to compute marginal likelihoods. Specifically then, what we are doing in RevBayes, how to compute marginal likelihoods, that we are then going to do in the tutorial this morning, estimating Bayes factors. So again, a different example is here. If we have just this topology, and our first model would say we have a constraint topology, that the chimps and bonobos are constrained. There's just one topology possible, and that has a posterior probability of 0.7, or it's unconstrained, so then we have the 3 different topologies. But so which of these models would be the best one? And we could just say, well, the maximum likelihood estimate, in both of these scenarios, we would actually get the same estimate. So if you just make the model that you have more complex because you add more parameters, like here the topology to vary, you could always get at least the same likelihood estimate, the maximum likelihood estimate as in the simpler model, but then we just need to additionally penalize for the additional parameters to find which of these hypotheses was more probable. So the first scenario, first test case that we can have in maximum likelihood estimation is that we do the likelihood ratio test. And the likelihood ratio test is we are computing the maximum likelihood estimate of under both of our models and computing the difference, or twice the difference. And this is the delta for the likelihood ratio test. And we can do that if the models are nested. That means that one model is a special case or a simpler model of the other model. And then we can say that this test statistic delta is approximately chi-square distributed with degrees of freedom as the number or the difference of parameters between those 2 models. And yeah, so we can then use this test statistic to select between model 0 and 1. Generally in phylogenetics, what we would do, we take our original data set, we have the 2 candidate models, we do maximum likelihood estimation, we get the likelihoods under those 2 models, compute the delta. Sometimes just the problem here really is, what is the significant delta that we have? And as I said before, we could just do assume that it's a chi-squared distribution, the delta, with the degrees of freedom. But it also has been shown that that is not quite appropriate always for phylogenetic models. So what we can do instead is we can simulate on our models that we have. We can simulate data, and then under the simulated data, we calculate the test statistic. So that is then here we're getting the distribution of test statistics for many simulated trees, and then we compare to the test statistic that we computed under our empirical data set. And then we see if that test statistic falls out in the tails, and based on that we would accept or reject our null models. The second test that we can do in maximum likelihood inference is the archaic information criterion, or the AIC, where you can see that it's quite similar to the likelihood ratio test. We're again computing the maximum likelihood estimate, but then the AIC is computed by twice the log of the maximum likelihood estimate plus 2 times the number of parameters. And then you just order all the different models based on their AIC values, and you take the one that has the lowest AIC score as being the best model. It has the advantage that you can actually do that for non-nested models. And in principle, it should say that the best model is really the one that has the lowest score. The question is still if it's significant, and there's some significance thresholds that are used in the literature to then say if that value is actually the best one. You could also do as in the example before, you could also, like here, you could also do a Monte Carlo simulation, simulate new data sets, and then simulate what the AIC scores or delta AIC scores should be to get a significant AIC threshold to compute if it's significant or not. And then finally, the last of the 3 different model selection criteria in the Frequentist inference is the Bayesian information criterion, which is not quite really Bayesian, but nevertheless it's called like that. And here you're again computing minus 2 times the log of the maximum likelihood estimate plus the number of parameters times the logarithm of the number of data points. So this one here has a different penalization term, but otherwise it's basically the same as the AIC. So it has also the same type of properties. Then you can you can use it for non-nested models. You can rank it in the same kind of way. And in the end, the important part about this is that we can rank these different tests in a way that we can say the likelihood ratio test is slightly more, it's less robust than the delta AIC, and the BIC is the most robust or the most conservative of the three. And that really comes from, if you look at the 3 different tests again, that the likelihood ratio test was just using the logarithm of the likelihood, whereas the AIC uses plus 2 times the number of parameters, and the BIC uses the number of parameters times the logarithm of the number of data points, or the number of samples that you're having. So this really shows you that one can be more robust or more conservative than the other. And if you're applying all these 3 different tests, that might be the reason why one of these test statistics finds a different model compared to the other one, because it's penalizing more complex models more heavily. Do you have any questions so far about the maximum likelihood model selection? No. Okay. So the problem that from a Bayesian perspective we see with the testing of different models in the frequentist way is that we use always the likelihood function. We maximize the likelihood function, but we do not take into account any uncertainty in our parameter estimate. We always just maximize that likelihood function and then take actually the computed likelihood score, assuming that this is the single best estimate, like the single best phylogeny with the single best substitution rate parameters and branch length. In a Bayesian perspective, we're doing that slightly different. So in a maximum likelihood way, that is called the profile likelihood that we're computing. But in a Bayesian perspective, what we're doing is we're computing the marginal likelihood. So instead of just finding that point over here that gives the highest likelihood, we're actually going to integrate over all parameter values to then compute the marginal probability or the marginal likelihood of the data over all different parameter values. And in that sense, we're trying to take really into account the uncertainty of all our data, and we're weighting the parameter values by their prior probabilities. So in the case that we had before here, that tree would have a marginal likelihood of 0.7, but then in this case here, because we have 3 different topologies, if we assume that all topologies had a prior of 1/3, so had the same prior probability, we would just sum up all these priors together, and then we would see that here the marginal likelihood is actually quite a bit smaller than in the first example. So we can use that information, the computing marginal likelihood, to compare which of the models is more probable. And that is really the idea what is behind Bayes factors. So Bayes factors, what we need to do here, we need to look again at Bayes' theorem. Yeah, like yesterday, John explained, we are usually interested in the posterior distribution. We are specifying the prior distribution, and we always have a likelihood function. And these are the only parts that we're specifying and then computing. And usually, this is the part, the normalizing constant, that we are just canceling out in our Markov chain Monte Carlo analysis, because we're only interested in the posterior distribution. Now, for model selection with Bayes factors, we are actually interested in this part here. So we actually need to compute that marginal likelihood, that normalizing constant, and that is really complicated because we need to integrate over the prior and all the likelihood values that are possible to compute that marginal likelihood. Just a little bit about Bayes factors. So the Bayes factor is defined as the probability of the data given hypothesis 1 over the probability of the data given hypothesis 0, which you can also rewrite as saying like the probability of the posterior given the hypothesis 1 divided by the posterior of the hypothesis 0 times the inverse of it, of the prior. So the prior ratio is then the prior of hypothesis 0 divided by the prior of hypothesis 1. So in this case, we could just, because we computed the marginal likelihood, then we have the Bayes factor of the model 1 divided by model 2, and that gives us here in this case a Bayes factor of 2.1. Now is the question, which of these Bayes factors is actually significant? So is 2.1 a large value, or is 2.1 just sort of an intermediate value or not? And for Bayes factors, there's this table that was developed to actually look if a Bayes factor is, if it's smaller than 0.1, it's very strong evidence for model 2. If it's between 0.1 and 1/3, it's a moderate evidence, and so on. So there's always these tables, which we always provide in the tutorials, and then you can directly look at the Bayes factors and decide, depending on how large the Bayes factor is, if it's a strong evidence or not for a given model. The only things that you have to consider when you're looking at these tables is that right now here I actually show the actual Bayes factors. In a lot of cases we are computing the log Bayes factors. So then these values are just log transformed. You just need to find the right column in those tables. Or another way people are often reporting Bayes factors are like the 2 times the Bayes factors. So just changing the values again, but the meaning remains exactly the same. So how do we compute marginal likelihoods in a software like RevBayes? Because this integral, the marginal likelihood that we want to compute, is very difficult to compute, or we can't actually compute it analytically. So the marginal likelihood, again, is the probability of our data given the model, marginalized or integrated summed, so summed over all trees, integrated over all branch length, over all the parameters, like all the substitution rate parameters, all the speciation extinction rate parameter, clock rates, and so on. So what we could do is, if we would assume that this is our posterior distribution, and then the red line is our prior distribution. To compute the probability, we could just use standard Monte Carlo sampling. So we could just simulate from the prior distribution and then compute what is the likelihood and just average it over the samples that we computed. But if you have a posterior distribution that is peaked as this one, how many samples that I simulate under this red prior do you actually think would hit that posterior peak? It's probably 0, right? Like here's some examples given, like 2 samples here, 2 here, 4 on these sides. We're probably never going to hit that one. So that's why we can't just use standard Monte Carlo sampling, where we would simulate from the prior to compute what the marginal likelihood is. So we need different types of algorithms that help us find where that posterior peak is and then weighting our samples appropriately. So for example, we can just, if that is our posterior distribution again, we can build then more an importance distribution and then sample from that importance distribution, compute the weights that the importance that we use for the importance distribution, reweight it, and then we actually get the weighted samples so that we can use this to approximate what the marginal likelihood would be. One way how to do that also was we originally used the harmonic mean estimator, which was used for quite a long time in phylogenetics to estimate marginal likelihoods. And you could compute the harmonic mean estimator directly from the output of the posterior distribution. So you were just running a standard MCMC analysis, and then you took the likelihood values and were just computing that harmonic mean, where the x1, x2, and so on, those are the likelihoods of the samples that you were using. So that's a really simple estimator, but the problem with the harmonic mean estimator is that it has an infinite variance, and it has been shown that this estimator is not really good and stable, and prefers actually more complex models. It's not penalizing more complex models enough. So it's not a really good idea. A different approach that we could also take is we could use reversible jump algorithms, which we have also implemented in RevBayes. And the idea between reversible jump algorithms is that we have two different models, like in the example that I showed in the beginning, where we have a speciation and extinction rate and want to test if that is correlated to like CO2. I could say that the simple model, or one model, has a correlation of 0, and the other one has a correlation that is drawn from my prior distribution. So then I use reversible jump to jump between model 1 and model 2, and depending on how often I sample which model, that gives me then directly the posterior probabilities of the model. And as I defined before, from the posterior probabilities of the models, I can directly compute what the Bayes factor is. I just need also to compute what the prior probabilities of the different models was. Generally, you would just say that the prior probabilities of different models is like, we say every model has the same prior probability, so that would cancel out. The problem for reversible jump algorithms is that they mostly work only in specific samples or for specific types of models, and we need specific MCMC moves that move from one model to the other model, and they are not always efficient. So in some cases, they can be very efficient if they work. If they don't work, you're out of luck. The next approach that we can also do to compute Bayes factors is by using mixture models, where we're setting up two different models, and then we're saying that the data is drawn from a mixture of model 1 and model 2. And then we say the probability of the data is, if we say it's a like equal mixture, it's 0.5 times the probability of the data given model 1 plus 0.5 times the probability of the data given model 2. And then we can use the MCMC to accept or reject from which model actually the data comes, so we can compute the contributions of those probabilities. And in that way, we can also weight which model, or what's the posterior probabilities or the marginal probabilities of the two different models, which then again gives us a very good estimate, or a very easy estimate of the Bayes factor. This also can be applied, or has some advantages and disadvantages. Quite often is if the models have a very strong marginal likelihood difference, then those mixture models don't really work that well, because they are not sensitive enough between, they would put all the mass on one model and no mass on the other model. So mixing the parameter values over the second model would be very difficult, and you're getting very unstable estimates. So the more general approach, and the approach that we are going to do in the tutorial, is we are going to approximate marginal likelihoods by an algorithm called stepping stone sampling, which is very similar, or in principle we are going to use the same type of machinery as for path sampling. So what we are going to do there is we're running an MCMC with a likelihood raised to the power of beta. So here we have the standard likelihood that we are defining, and we are just raising the likelihood by the power, that's the posterior, and we are raising the likelihood to the power of beta times the prior. If our beta is 0, then that is just, then we are just at the prior, and if our beta is 1, then we are at the posterior distribution. So this is really the path that we are sampling to. This figure is also just showing what these different paths represent. And then for all the different beta values that we're using, we are computing what's the probability of, so this is our posterior distribution. Then we compute the estimate, the mean estimate of the posterior for a beta value of like 0.38, and then of 0.1. We compute those ratios, And as you can see here, these ratios, they actually canceled out. So in the end, what we are getting is just the ratio of the prior over the posterior. So we get directly the marginal likelihood from this. If you want to imagine that a little bit more from by the posterior distribution that we looked at before, as the red line again was the prior distribution, and the black line was the posterior distribution. So we start by sampling directly from that black line, the posterior distribution. Then in the next step, we're going to the blue distribution that goes a little bit wider and tries to go more towards the prior distribution. Then we go to the green line and then to the orange line, and to step by step these different samples. So what that really means for the analysis that you're going to do is basically that you're running an MCMC algorithm not just once to estimate the posterior distribution and the phylogenetic trees and the parameters under the posterior distribution, but you're running in a shorter MCMC under the posterior, then under the next value of beta, then for the next value of beta. So usually like for 20 or 50 or 100 different values of beta, you're running short MCMCs. You're combining all this output to then get a marginal likelihood estimate. So all these algorithms are very computationally expensive, and that's why it's a little bit more tricky or more difficult to use them, especially on large data sets. But unfortunately, that's sort of the best solution that is currently available. If we compare path sampling to stepping stone sampling, so they're actually using the exact same sort of stepping stones that we're doing for stepping stone sampling and path sampling. So we can do in one run just estimating once these power posterior distributions raised to the different beta values, and then we calculate the path sampling estimator and the stepping stone sampling estimator really cheaply once we have done those power posterior estimates. It has been shown, or it's generally said, that the stepping stone sampler is slightly more robust than the path sampler. But what we are generally recommending is that we're going to estimate both the path sampling estimator and the stepping stone sampling estimator, and they both are guaranteed to converge to the true marginal likelihood. So if both of them give the same result, then I would be happy that your runs seem to have converged. If both of them give different estimates, then I would be more concerned that one of them hasn't worked properly. So you should run the entire MCMC and power posterior analysis for more steps in your chain. Just as the final overview, so for frequentist inference, we had likelihood ratio tests, AIC, BICs, but they are a little bit unreliable if we just have fixed values that we use as a threshold. So also in these cases, we need to find what a good threshold is. And that's when we would suggest to use Monte Carlo simulation to find what's the significant cutoff that you can use for these tests. Bayes factors are generally much more robust for testing or selecting different models, but they're very slow to compute. And also Bayes factors always depend on the priors that you're choosing, which means that if you're specifying one model, let's say with an exponential distribution with mean 10 on the branch length, that is one model with one set of priors, and a different model could be this exact same model, but where you would say my prior distribution is an exponential distribution with a mean of 1, and you're just testing these different priors, and the priors always can have a strong impact on your Bayes factors. So here the priors are much more important than what you're actually doing for estimating your posterior distribution. And the general recommendation there is also, if you notice that the prior has a really strong impact on your Bayes factors, then you could just sort of double or half the prior mean and test what the difference is and how sensitive your estimates are to the prior, and if that could be a reason why you're getting certain results. So there's some care you have to take if you use Bayes factors. There's different types of Other approaches than the stepping stone sampler, like reversible jump, mixture models, or DPP, they can help quite well if you have a model that you can set up in that specific way. But the problem there is more poor mixing. Otherwise, the analyses are generally much faster than using stepping stone sampling. But stepping stone sampling is in general the safest way to do. Or finally, you could also use hierarchical models to test between the different, testing between different models. So, are there questions about model testing, or specifically about the model selection part? The general goal for this session, or the tutorial for this morning, will then be that we are computing the stepping stone samplers to estimate the marginal likelihood, and then you can look at the Bayes factor table to select between the different substitution models. For this course here, we have now the session, the model selection, and the tutorial that we're doing is the RevBayes factor tutorial. That tutorial, so this tutorial again, well, that one is using, again, the same data set that we're using yesterday. So it's really used as a repetition to understand what we did yesterday, and where you can just continue also what we tried yesterday, and then switch over to this tutorial. Yes, a little bit of an introduction and overview given again what the Bayes factor is. So it's we compute the posterior odds, where the posterior odds is just given here as the marginal probabilities of the data given model 1 and model 2, and then you also have the prior odds. So the Bayes factor is the posterior divided by the prior. I switched that here around in my slides, just saying times and then the inverse of that ratio. Then we have here the table. You can see these are the standard Bayes factors, the log Bayes factors, or the log 10 Bayes factors, depending on what you're computing. In RevBayes, you will always get the output as the natural logarithm for the Bayes factors. And you can see then if it's decisive or not. So the purpose then for this tutorial is that we have these 5 different substitution models, the same as yesterday. So we have the Jukes Cantor model, the HKY model, the GTR model, and plus gamma and plus I variants of it. And we want to test which of these substitution models is actually the best model for the given data that we have. So here we have a little bit more instructions. And the main parts that we need to do is, instead of running an MCMC analysis like we did yesterday, so we are specifying exactly the same model as before, but the only difference that we do is then we're creating a power posterior object instead of the MCMC object, give it the model, the moves, and the monitors. So in that sense, exactly the same as yesterday. And then we provided the output directory and the number of categories, where the number of categories just means how many different beta values are we using. So how many different stepping stones or power posteriors are we going to use for this power posterior analysis. Then we're running, as for the MCMC, we are going to run a burn-in, and then we're going to actually run that power posterior analysis. And once we have done that, the last things that we need to do is we need to read in the output file that we specified here. We read that in again in the stepping stone sampler, specify what the column name is where the powers are stored, and specifying where the likelihood, the name of the column where the likelihood values are stored is. We could have omitted that part in RevBayes because that is always hard-coded in there. But the nice part here is actually that we enable these features. So for example, if we were using Beast or Mr. Bayes, and produce power posterior samples from those softwares. You can also read them in RevBayes and compute the stepping stone sampling estimator or path sampling estimator from the output of other software. And they use different column names by just some weird definitions. Okay. So here we would do exactly the same thing for the path sampling estimator, just exactly the same as for the stepping stone sampling estimator. Then we use this member method to compute the marginal probability. So as an example, we have the juxcante.rev script. So this is our example here. I can quickly go over that one as well again. So the first part, you were reading in the character data exactly as we did yesterday. So we're reading in our data. So let's start with reading in the data, nothing new from that. And then we're getting the number of species and computing the number of branches so we can set up our branch length for every single branch in our tree. So that's why we need to get the number of species, and we need to get the taxon information to specify, or use that to specify the prior distribution on our topology. So that way it's really the same parts as we did yesterday. We're also specifying our index for the moves and the monitors. And then we're setting up our substitution model where we use the juxcante function and just tell it that we have 4 different states. So this is again our substitution matrix. We're specifying the outgroup using the flying lemur and specifying a prior distribution on the topology. So as the prior distribution, again, we just use a uniform probability or the same probability on every single topology, having a uniform distribution over all topologies. We're applying the same type of moves as yesterday, so the nearest neighbor interchange and the SPR move, the subtree prune and regraft. And then we're specifying the branches in our loops. So we're going over all the number of branches. We're creating a variable for the BL variable drawn from an exponential distribution with a mean 0.1. And we are applying a scaling move on that branch length variable. Since we are really going to do exactly what we did yesterday, we're also specifying, or we're computing the sum of the branch lengths, so to know what the tree length is. And this again here is a deterministic variable because we use the colon equal, and because the sum is just a deterministic computation, there's no randomness involved. That's why again it's a deterministic variable. The same as for the tree assembly, because it's deterministically once you have the topology and just set the branch length to it. It's not just randomly adding the branch length, it's really just deterministically keeping the branch length matched by index. And finally, we're creating our follow CTMC object and clamping the data to it. So the last parts are that we're creating our model, because we need to, for running the power posterior analysis, we need to have a model, we need to have the moves, and we need to have the monitors. So we already created all the moves on the fly just when we were creating the random variables. So we're going to create the model now here as well, just passing in any of the variables that we created. That did not quite work.
Yeah, I was getting the same strange thing about the abstract and all these discrete things showing up.
Okay.
It's when you're copying from the text editor, and there's some new line characters and things.
Okay, if I typed it again, it worked. Let's see if the model was actually created. It looks fine. Yeah, might be from the text editor. Just from, yeah, because we're here directly doing it from the web. So I was running those scripts a few days ago and they looked fine just directly, because we could just use, again, like yesterday, just using the source command to run that entire script, and that always should work. So this is just for me when I go through the entire tutorial through that example script to explain what these different lines actually mean. Okay, and then we're going to run the power posterior analysis. So this is the heavy part here. And in this case, we are specifying that we're going to use 127 different categories. The reason why we're doing 127 is you could try it a little bit if you want to use longer MCMC runs or more categories to get more stable estimates. 127 works out that it's actually more on the side that we use a lot of them. We could increase the number of generations as well. So let me just start that while I talk, because that will take a little while. Also 127 actually adds up to 128 analysis, because we do once under the posterior, plus then the 127 different categories. So it's 128 in total, and if we wanted to distribute that on a cluster using MPI, 128 is nicely dividable for if you have 16 cores, something like that. So you get a lot of speed up, because then you can do the stepping stone sampler on all the different stepping stones, distributed on your cluster on all the different cores, so you get a lot of speed up if you have a large or good machine at home. Exactly, yeah. So these are the only changes to yesterday. Everything above was the same. The only difference now is this part here to yesterday. That is what I meant by we're going to repeat a lot of what we did yesterday, so it will be really useful going just through those parts again. And if you want to change then the different models, you just need to go in here and change your different substitution rate matrix in the same way as we changed yesterday.
How do you assess convergence?
So what we implemented here is that the power posterior, give me a second here, it is, I'm running it in the Bayes vector tutorial, so there's the output, and you have the output. This is just the likelihood output. So if I would look in those, so this is just where this is the current sampled state. So we already removed the burn-in part here. This is the power. So I was actually sampling from the posterior, and those are the posterior or the actual likelihood values. This is the first values that we're getting. But then we're also getting, for every single one of them, we're getting a file, and we're getting output files like the MCMC that we specified, that we specified in our monitor here. So I specified it primates _ site B _ jukescanter.log. So to assess convergence for them, what we could do in these cases, we're getting first, for each one of them, we're getting a log file. So we could assess convergence for every single MCMC on every single stone that we're doing, if you're concerned that there's convergence issues. The more rough way to assess convergence would be running the power posterior estimations 2, 3, 4 times, and then seeing if you get the same marginal likelihood estimates. So for me, as a just rule of thumb would be if you run it twice, you get exact the same values up to, let's say, 1 or 2 digits. That should be fine. And the output that you're seeing here, that step is always saying this is a one stepping stone and it's running here number 60 out of 128 and so on. So this is just the output that you're seeing. These outputs are much faster than what we were seeing yesterday when you were running the full analysis. And the difference is because we are saying we're only running it for 1,000 generations. The reason is why we're running shorter MCMCs for the stepping stone sampling is that we are not actually interested to get a very good estimate of our parameter estimates, of the posterior distribution of our parameter estimate. We're only estimated to get sort of a good sample, a rough good sample of the likelihood for a specific stepping stone sampling. And the theory for the stepping stone sampler was originally saying we just need one single sample as a proxy from for that stepping stone, so for that beta value. But we, of course, we take more samples and take then the average of them to get a much better estimate. So that is why 1,000 or like 10 times less samples, or maybe 50 times less than for an actual full MCMC could be sufficient for power posterior analysis. That's why it doesn't let it explode too much. We're still using quite a strong burn-in because the burn-in, that's more the difficult part in the MCMC analysis. We first need to converge to the posterior distribution. And then once we have that difficult part that we converge to the posterior distribution, the stepping stone sampler, it's actually easier to just randomly walk away from that posterior distribution again, because once you're going to those stepping stones, that where the power goes towards zero, so where it goes towards the prior distribution, it's much easier to just randomly walk away than to find that one narrow peak of the posterior. That's why this sort of setting works efficiently and usually stable enough. So we are almost done, which means I can just copy those lines to compute the two different estimates of my marginal likelihood. Yeah.
So you need to know the posterior first before you can do the stepping stone.
Right.
Why don't you need to first run a long analysis like we did yesterday to make sure you're converting on the posterior?
Well, this is why I'm running the sort of a long burn-in. And my burn-in, well, for this small example, it's only 10,000. But even for most examples or most data sets in RevBayes, because we're doing many moves per iteration, doing 10, 30, or 50,000 would be sufficient. And that's the case where you should have converged. So yeah, in principle, you're doing first that really long run, and then you can do shorter runs.
And so you would do the model selection, and once you choose your model, you would then do a long CMC run to actually get your parameter estimates?
Well, there's two ways. One way would be exactly that. The other way is what is also nice currently with our output, that you saw the first stone is already sampling from the posterior distribution. And since we are storing all these outputs, you actually have those samples from your posterior distribution directly there. They're a little bit short runs, so we could, for example, where's my tracer? I could just take this output and log in what the tree length was. So I get a tree length distribution. There's something not quite working. That is not a good example to show. Okay, I need to check what is happening. So here I will check that later. But for that tutorial, so now I was pasting in to create a stepping stone sampler object and compute the marginal likelihood under that stepping stone sampler. And then I used the path sampler object to compute the marginal likelihood here. And you're seeing that both of them give pretty much the same estimates, where it's just the difference of 0.05. Well, I would say like that's just stochastic error. That's usually fine. And you don't really have to worry much about it. If the difference is even like 0.1 or 0.2, that's, I think, okay, and you could either just go with a stepping stone sampler, or you take the mean of the two, or just run it longer, something like that. But it's sort of in the baseline, or it should give you a good estimate. Sometimes it's a little bit interesting that when you see you're getting very unstable estimates, because already 2 units difference for the log likelihood units is already a strong signal for one model over the other. But sometimes you're getting these like small difference just because of the stochasticity of that stepping stone or the power posterior algorithm. So if 2 models are very similar, then you might really need to compute those values very precisely. As you will see in these examples, they will be so different, then the ordering of the different models will not like depend on the second digits here. So yeah, I suggest that you just keep going through that tutorial and try to go through that, estimate the marginal likelihoods under different models. And there should be a table then here. It says that you should do that under the different substitution models, and then put in the marginal likelihood estimates under them to compute which one is the best one. And then finally, here's a little bit of explanation of once you actually have the marginal likelihood, how you're computing the Bayes factors. So then you can compute that entire table or fill in the table with all the Bayes factors. And there's a little bit extra information that I was also mentioning in my introductory slides.